powwow and then try to make them come back inside. If you're going to skip, they're going to leave. So, oh, dang, am I being recorded? Hi, everybody. Nothing going on here. Going to go back to the slide we were on.
They're also teaching powwows for those who have failed.
The first few questions on Magnetism 2 go over this right-hand rule stuff again, so I'm going to re-go over it. I'm going to go over it again. So, magnetic field goes from north to south, as the PowerPoint said before. So this is the north pole, and this is the south pole. So the one it's going to is going south, from north to south. That's the way magnetic field goes.
Speed.
Okay. Wait, did you say speed or sped?
Speed.
Anyway,
Speed.
let's go. Let's do the assignment. All right. Right-hand rule, you remember it? I really do like that mood lighting. Look at that. Uh-oh!
What?
Are they going to come back on?
Miss Thorley is not back. Where's she at? No, the intercom didn't work.
So, just like I had y'all do your, pretend you had a wire coming out of your desk, that's what this person's doing. Wire's going straight up, so they point their thumb in the direction of the current. Remember, moving electrons are current. That's what electricity is made of. And moving electrons, current, create magnetic fields when they move. And if you point your thumb in the direction of the current, your fingers show the direction of the magnetic field. So this guy's fingers are curling around this way. So if you look from the top, the magnetic field goes curling around counterclockwise. Not to give away the answer, but please answer this question before continuing. What would happen to these compasses if this current were going up? Use your right-hand rule. Pretend like you're grabbing this wire. Which way do your fingers show these things, these compasses pointing?
Counterclockwise.
South.
It's clockwise or counterclockwise. And you can tell which direction they are by looking at a clock.
Well, and by using the right-hand rule.
Yeah.
Pretending that your fingers are a clock.
So the north is going to be like
Or
at
not.
the top, the bottom one's going to be south.
So is this like today's work from the slides yesterday?
The first few questions of Magnetism 2 are from yesterday, just to refresh our memories. And then we're going to stop and do the right-hand rule assignment in a minute as we get to the end of the slides here. Because I don't want to start with the left-hand stuff.
How
Because
long
there's
did it
left-hand
take you
rule.
to
Did you
make
know that?
these Google slides?
Huh?
How long did it take you to make the Google slides?
Well, this was a pre-existing thing. I didn't make this PowerPoint, but I did a lot of work to edit it this time, since it's a lot of people's only resource, maybe. What if they can't watch the video? Anyway, tried to make it as inclusive as possible of the things that I said. Some things I normally say on the slides, I put them, I typed them actually in the slides. Anyway, we're on video right now, so I got to keep going. If you do your right hand, make sure you use your right hand. It's an easy mistake to make that I almost did, was you don't use your left hand for the right hand rule, then it doesn't work. Use your right hand, your fingers show it goes around counterclockwise, just like I kind of gave away the answer to before. So, with the right hand rule, we are going to figure out how electromagnets work. That makes sense, right? Moving electrons, that's electricity, that's current. If that makes a magnetic field, then that's all you need to make an electromagnet. I mean, that would be real simple. Data, are you working on this? Make sure you're doing Magnetism 2 or paying attention up here. So look at this. It's a little loop. The current, the electrons, move this way, and then they go over here, and then they go down there. So if you use the right-hand rule, you can see, okay, right here, whoop, my fingers show the magnetic field. My thumb's pointing in the direction of the current. My fingers show the magnetic field is going counterclockwise, like we just did, because it's going the same direction. The current's going up again. And then, if I keep my thumb pointed in the direction of the current, up here, I don't think that's actually the magnetic field noise, but my fingers show the direction of the magnetic field again. They go there and there. So it's going into the middle of the loop, just like it was right there, into the middle of the loop. And then down here, whoop, my fingers are still pointing in the direction, but my thumb's still pointing in the direction of the current. My fingers are still going into the middle there. So at each point around here, you get a magnetic field right through the middle that's going that way. And at each point that it makes a magnetic field, it adds up in the middle, so there's a stronger magnetic field in the middle where they're all adding up. You can tell it's in the right-hand rule. So this is the basis of how an electromagnet works. There's more to it, so hold on. Stay tuned for details. This picture is not as good in my opinion, but I just wanted to include another picture because it's difficult to depict these three-dimensional things on two-dimensional paper when the current's going this way and this thing. I always imagine it going in like this, and then you can't even see these little dots. This is a solenoid. We're still on electromagnets. We're going to use this to make an electromagnet. But it's something that has a bunch of loops in it, and electricity goes through it. Solenoids can be used for some different things. We're going to use it for an electromagnet. So what this picture is trying to show, it's a real difficult to draw thing because it's all supposed to be three-dimensional, but we only have a two-dimensional surface. So it's got a bunch of loops. We had one loop before, and we saw in the middle of the loop, it created a big old magnetic field. This one, a coiled wire, has a bunch of loops, and each loop is making a big magnetic field through the middle, and then this loop is adding to that magnetic field, and the more loops you have, the bigger a magnetic field you can have. And you can use the right-hand rule to figure this out. See which way is the current going. This way. This way. It's making it go through the middle there. We'll be able to tell better soon. So we can actually do this. We're not doing this today, but maybe tomorrow? Question mark? You can make an electromagnet. See, the more loops you have, the stronger your magnet is. So this has a whole bunch of loops. Now, this wire isn't just metal. It has an insulation on it. That's important because if the wire is touching the other wires here, you can't have electricity just go, well, I don't have to go in a loop. I'll just go like this. If it does that, then it's not traveling in a loop, and it won't make an electromagnet. But if you take a nail and wrap insulated wire around it and connect some batteries over here, you can totally pick up some stuff. It's got to be some small stuff because we're just using batteries. But you know, it's good for safety for a demonstration. But we'll try and do this tomorrow, I think. So yeah, you put more loops on, you get a stronger magnetic field. You put more batteries on, you get a stronger magnetic field. And there's one more thing. It depends. It makes a difference what's inside the loops. So we've got an iron nail here. That's going to work real well. If you have a plastic nail, it's not going to work as well. And we'll get to that in a minute. So this is telling what, how to make the magnetic field stronger. The magnetic field, capital B, measured in Tesla with a T, capital T. Magnetic field is proportional to the number of loops in. So more loops you have, the stronger magnetic field is. Magnetic field is proportional to capital I for current. So the more current is going through your wire, the stronger your electromagnet will be, the magnetic field from your electromagnet. And your magnetic field is proportional to the permeability of the material that's in here. And we'll talk about permeability in a minute on the next slide, I think. So it makes a difference what's inside there is all. This is just another way to say what I was saying on that last slide. Are y'all answering that Uh,
How do you make
what is an electromagnet? How do electromagnets work? Question.
How do you make them?
How do you make electromagnets?
Yeah.
That's just this picture. You do this stuff. Batteries, insulated wire, copper, iron nail.
Oh, wire run iron.
You
Yeah.
basically
Make
put
one of these.
electricity into
Use these
a
materials,
solenoid.
do what they did.
Put a bunch of current on a piece of iron.
Yep. Permeability. So, I want to talk about the traffic lights. You guys know about traffic lights? Traffic lights, you can see where they cut up the pavement to put the sensor in, right? That sensor does not work, has nothing to do with the weight of your car. It's not pressing a button underneath the pavement when the pavement bends a little bit or anything like that. It works because your cars are usually made of metal. A car's not made of metal, it's not going to trip the traffic light, even if it's heavier than a normal car. Because traffic signals have a buried solenoid down there, and that solenoid is an electromagnet. It induces it induces a magnetic field inside your wheels and the frame of your car that's next to the pavement. When it does that, when it makes a magnetic field in another material like that, that changes the voltage in the solenoid, and it's got a little voltmeter down there. And when that voltage reading changes, that's what trips the light.
So the more metal you have on your car,
More likely.
the more likely you're gonna
Yeah,
Like,
yeah.
strap animals to your car. But
That's why, if you pull up, if you miss the white line and you pull up way past the white line, like, or if you stop way behind it, like people like to do over at the junior high, then you're not going to trip the light. Now, some new lights do work with the camera, not the kind that gives you a ticket. The kind it's a camera that has a computer in it, and it recognizes when the shape that it sees is a car, and where that shape is, and when it needs to trip the light that way, which is a cheaper, more efficient way to do it. But kind of cool. So it depends on what your car's made of, though. Some materials are easy for that solenoid to make a magnetic field in, depending on what kind of metal you have. Like, people with magnesium wheels, it's probably not quite as good, but their car is still probably made of steel, so it's fine. So permeability is how easy it is for a magnetic field to be formed inside that material. So like if you have a plastic car, plastic has very low permeability, so it wouldn't work as well. But yeah, so I used to ride bikes, and if the wheels on a bike are metal, the frame's kind of way up there. So if you don't trip the light, it helps to get off and lay down the bike, and then sometimes that helps. You put more metal close to the sensor. That helps. Here's some examples of things that have different permeabilities. So relative to the permeability of a vacuum, mu metal, a nickel iron alloy, can create a magnetic field that's 20,000 times greater than if there were a vacuum. So think about if that electromagnet diagram with that wire wound around that nail. If that nail were made of mu metal, that would be 20,000 times stronger than if there were nothing inside that wire, if there were no air, no anything, just a vacuum. Or if you put this nickel zinc type of thing inside there, if your nail was made of nickel zinc instead of nickel iron alloy, it would be 16 to 640 times, nowhere near 20,000 times the vacuum. Or if you have a regular steel nail, 100 times that. If you try to make an electromagnet with water inside of it, it's not quite as good as a vacuum. And superconductors, we'll talk about them later. All right, so if there's another right-hand rule question. I was very careful trying to talk about right-hand rule yesterday because what we learned is that your wire shows the direction, your thumb shows the direction of the current, which is going through a straight wire, and then your fingers show the direction the magnetic field curls around it. That's when your wire is straight. But what if you have a curly wire? Your thumb is not curly. I mean, I don't know if you could do that. Oh. Anyway, You can do it backwards too, is what this is saying. If you have a curly wire, your fingers always show what's curly. So in the examples we've done so far, the magnetic field's been what's curly, and that's what your finger showed. If the wire is curly, you can use your fingers to show that, and then your thumb shows the direction of the magnetic field. So your wire is, the current in the wire is going around and around like this, and that's what your fingers are showing. The magnetic field through the center of the electromagnet here would go pew, this way. So right hand rule can be used either way. In our assignment today, the thumb will always represent current, just to make things less confusing. But yeah, your thumb shows whichever one's straight, magnetic field or current, and your fingers show whichever one's curly, magnetic field or current. And they always show opposite things. Like your thumb can't show current, and then your fingers also show current. They always show opposite things.
What would happen if you put like one of those curly, like those solenoids into like a solenoid shape? Like,
I don't know. Like if instead of a straight wire that goes around and around, it's a wiggly wire, a curly wire that goes around and around.
yeah,
I don't
like
know.
it's a solenoid square.
That would be interesting. So, this little picture shows a moving charged particle. Here's a Q for charge, plus is its charge apparently. And it's going this way. So, that's a moving charge that counts as current. We can use the right hand rule to determine what kind of magnetic field will be created around it. So, phew, that magnetic field would go around it like this. Now, what we're learning now is, because I mean, we know a moving charge makes a magnetic field. This could be part of an electromagnet because it's a moving charge making a magnetic field. But what we're learning now is how electric motors work. And we'll get there tomorrow. But this makes its own magnetic field. It goes this way. There's already a magnetic field here. Remember, capital B is for magnetic field? All these X's show the direction of the magnetic field. I'm going to tell you how to use these X's. You guys know about archery?
Yeah.
You guys know of the arrows from archery? You know, they're like this. They're long stick-looking things. There's a point on one end, and there's feathers on the other end.
Yeah.
That's what these X's are showing. These X's are the feathers on the arrow, and X's mean that the arrow is going into the page. Because if you're looking at the page, you can see, if you can see the feathers, that means that it's going away from you. So this magnetic field is going into the page because you can see the feathers back here. The way it shows out of the page is it'll have a little dot. Like I've got the dot right here. Can you see it? Dot.
What do you mean it's going into the page?
Well, it's like the z-axis in math.
It's the third axis since 3D geometry has.
Yeah, 3D business. So like, you know, the vertical axis goes up and down, the horizontal axis goes side to side, that would be y and x.
Y,
Z goes into the page or out of the page. And that's what this is showing. This is, the direction of this is this way. They can't like point an arrow that way because then it would be going one of these ways. So that's why they use an X or a dot. So if it's a dot, if you see a dot, that's the point of the arrow. That means the arrow is coming toward you. And that would mean out of the page.
So if you see the X, it means that it's going into the page. If you see the X is coming, or the dot is coming out.
Yeah. Yeah. Excuse me. So yeah, this is a magnetic field going into the page. But this charged particle is moving, making its own magnetic field that goes around like this. The thing with this is, these two magnetic fields will interact, and it will make this charged particle move. The magnetic fields will attract or repel each other the way magnetic fields do, and it'll make the charged particle move. And that's what this green arrow is showing. It'll get a force this way. And there's a way to determine which way that force goes, but we're going to do that later. I'm not doing that yet. So this is like, if you have your phone charging or whatever, there's a magnetic field. Like if this is the wall and there's your phone, there's a magnetic field around that wire. If you put a magnet next to that magnetic field, you can interact with the magnetic field that's already there, and you might be able to deflect that thing. If you unplug that wire, it might not work as well. But don't try that. I don't know if that's quite safe. That's a theoretical thought. Yep. And I think that's it. Oh no, there's 2 more slides. Okay. So this is how to calculate how much force is going to result from those 2 magnetic fields interacting. The magnetic field from the moving charge and the magnetic field that's already there. So here's the charge, here's how much it's moving, velocity, Q for charge in coulombs, V for velocity in meters per second, capital B for the magnetic field that's already there in Tesla with a capital T. And it tells you all those things. FB is force of the magnetic field. That's why they got that capital B down there. That's the variable of the magnetic field. Jada, will you get the door, please?
I got it.
No, Jada needs to get it.
I did it.
I think they're here for Jada.
What?
Get the door.
What is down there? There's something on my PowerPoint. What's that? Can you see that? Oh. It's for you.
For who?
Jada,
What?
it's for you when convenient.
When convenient is right now convenient?
Yeah, that's fine.
What?
Where you go? I don't know.
There's
That's
something here.
It's called Ooh. Oh.
There's something right there. You see it? Look. Oh, whatever. We already know this, but so this shows what base units Tesla is made of, the unit for magnetic field. And I guess coulombs and newtons aren't base units. Newtons are made of, it's force, right? Mass times acceleration. So it's made of, mass is kilograms, acceleration is meters per second squared. So newtons are actually kilogram meters per second squared. But this is what magnetic fields are made of, these units. We could break them down further with newtons and coulombs, but let's not. That's complicated. But you can see they're actually newton seconds per coulometer. If you think about a magnetic field, it kind of makes sense, because magnetic fields are caused by moving charged particles. You got your charge here, you've got a distance here. I suppose it moves a distance, or the magnetic field extends a distance. So I can see how coulombs and meters both have something to do with magnetic field. And then newton seconds. Well, newtons are force. Magnetic fields can have force when they interact with other magnetic fields. I'm not sure about that, but anyway, that's what Tesla is made of. That's what magnetic field unit is made of, is Tesla. And do y'all have any questions about any of the questions on magnetism 2 that you didn't get when I went through it? Everybody's good? Alan, you good? All right. So there's another assignment where we can practice our right-hand rule stuff. Please go to that right-hand rule assignment. No problem. Y'all have plenty of time to do that.